So it's obvious. Hopefully, it's obvious that we are creating weather and climate to basically deal with this distribution of energy with surplus here and deficit here. But then that's in a very broad sense. Then we have to add the details of what that means in terms of the wind winds that vary from the tropics to the poles, the pressures that get created, the evaporation that happens, the precipitation that happens, ocean currents that get generated. Atmosphere has no boundaries, so winds can go around and around, whereas ocean has boundaries, so that creates a certain specific characteristics in the ocean circulation. And Earth is rotating, so we have to add rotational effects, which we already kind of implied without saying exactly how that occurs, but I think most of you are probably exposed to Coriolis effect at some point in your basic education. So we'll sorry, I'm having hiccups and I'm being a clumsy drinker. So we will talk about Coriolis a little bit again. So looking at this deficit and surplus, let's see how the energy transport happens. So basically it's this difference that has to be moved. So that's how it appears, symmetrically being moved away from the tropics. Actually not perfectly symmetric. You can see here it's hitting the value of 6 petawatts, whereas here it's less than that. So there is an asymmetry. Everything is hemispherically asymmetric because Antarctica is continent on the pole, completely glaciated, whereas Arctic is an ocean with sea ice and ocean that, and land is much more in the northern hemisphere than in the southern hemisphere, etc. So you have to basically, so this is increasing heat transport towards some mid-latitude and then decreasing transport, increasing transport and decreasing transport. These numbers are negative because you're moving heat in the southern direction. So if you imagine an XY axis, Y will be positive towards northern latitudes and negative towards southern latitudes. It just means the concept of direction is positive and negative, so heat transport is still towards the poles away from the tropics. So you need to move this energy here, and then the energy transport has to go to 0 at the poles because you are basically integrated energy under these curves is what is reaching there from the low latitudes. So seasonal variations in insolation, just repeating ourselves, the amount of radiation reaching the edge of the atmosphere in the polar regions is maximum in the northern hemisphere. So we have to be careful. This is the northern hemisphere, so you are peaking in the northern summer, and then it should go to 0 in the winter time, and in the radiation reaching the Earth's surface is going to be affected by all the greenhouse effects that we talked about. So again, you have this peak in the summer and minimum in the winter. So this is in the temperate regions, so these are polar regions, temperate regions. So again, northern hemisphere bias here, so peak in the boreal summer months, and tropical regions have a little dip here because we will see that the what I already mentioned, deep convection when the heating is maximum is going to create cold cloud top temperatures which are going to reflect sunlight and also reduce the amount of energy received at the surface, which also resulted in minimum in OLR locally, as we saw before. The other concept that we will need, we kind of implied this when we did energy balance, but this is the shortwave radiation. Depending on how hot it is, sometimes you can see the flames. If you imagine, for example, an electric stove, you can leave it on low flame, it's getting warm, but it's not showing any color. But when you have warm fire, then you can obviously see the fires, and you can put your hand here and you can feel the heat because it's radiating out energy. And it's warming a pot which is getting heated directly by the fire, and since it doesn't reach these temperatures, it's not going to start shining bright, but it's going to transfer that heat by conduction to the handle here. For example, in conduction, it's the vibration of the molecules. So as temperature increases, remember before we saw temperature in the atmosphere where we said molecules acquire energy and they vibrate, like in the greenhouse effect. They absorb photons of light and vibrate. That's the same thing. But the water inside is going to pick up that heat, and water molecules are going to begin to move because water is a fluid. So molecules at the bottom get heated first, they get lighter and they come up and they take the heat with them, and for continuity reasons water has to sink somewhere, so water begins to circulate. This is basically what happens in the atmosphere as well. Near the surface there is heating going on, air molecules get heated and they go up, and then new molecules have to replace them, so you end up creating circulations. And what matters most is things like specific heat capacity, typically used in measured in units of joules per gram per degree centigrade. It's the amount of heat particular fluid or substance can store for each degree centigrade change. So air is considered 1, then water has 4.2 times the heat capacity of air at constant pressure. So these things are details. You can also have volumetric heat capacity where you keep the volume constant. For fluids, that is a easier convention to shift between Cp and Cv. So Cv and Cp are related through density, obviously. So there it is measured in joules per meter cube per degree centigrade. So instead of mass, you measure it in volume. It's volumetric heat capacity, and density of course is measured in kilograms per meter cube or grams per centimeter cube, and so on. So for air it's 1 almost. For water it's 1000 kilograms per meter cube. So this is 1000 for air in volumetric heat capacity, and 4,200,000 for water. This matters a lot. We have already mentioned this before. So here the pot will get heated fast, the water will or milk, whatever, will warm slowly. When you turn off the fire, the pot will cool rapidly as well because its heat capacity is low, but the water will cool much slower. And this matters because when you're near coast, the land will warm faster during the day and cool faster during the night, whereas the nearby ocean will warm slower during the day and cool slower during the night. And the temperature is typically directly related to the pressure in the atmosphere. So warmer temperatures, lower pressure, colder temperatures, higher pressure, which means the pressure also changes rapidly on land because of its low heat capacity, and slower on the ocean. So during the daytime the temperature gradient will be one way, and during the nighttime it will be the other way. So the pressure gradients reverse, which means airflow will change because air will go from high pressure to low pressure, except we are on a rotating system, so I have to add Coriolis effect depending on how far we move and how fast we move. Okay, so in the real world, the pot and water analogy becomes like this: solar heating, visible radiation coming, heating everything, resulting in thermal radiation. So air molecules get heated, they rise, so they can create rising thermal. So in a desert, for example, you have lots of thermal winds like this. If you have a lot of moisture, then evaporation happens and warm air picks up moisture together with it, and it expands because we will see that the pressure decreases with height in the atmosphere. So air molecule, as it goes from higher pressure near the surface to lower pressure, it begins to expand. When it expands, it cools because of these gas laws. We have things like ideal gas law where pressure, temperature and density are related. pressure decreases, density decreases, temperature decreases, and so on. So then condensation, so water vapor condenses and releases the energy. Evaporation picks up the energy, condensation releases the energy. So this also drives a circulation. So cool air then sinks and fills the gap that is created by air that is rising. So you end up with these kind of circulation, which will expand to planetary scale and say that in the tropics air is getting warmer and rising, creating clouds and rain. It is hitting a ceiling. We will see there is a ceiling, and going away from the equator, also away from the convection, as we will see, and air is sinking at some latitude and coming towards the tropics. So we will see that this circulation also corresponds to circulations in the atmosphere. So slowly we are now going from energy to dynamics, thermodynamics to dynamics. So thermodynamics is this energy, rising air, condensing air, condensing water vapor, and dynamics is this circulation. So convection is when air molecules are moving the energy, and in the real world conduction is very small, so always convection and advection that move energy. Okay, so this is what that results in heating. As we said, temperatures create, warm temperatures create low pressure, so rising air, low pressure, sinking air warms, just like rising air cools and expands and condenses. Sinking air, pressure increases, it warms, and here even though it's warming, you have high pressure because air is sinking, so you have to be very careful how high pressure is created. Okay, so that means here warmer temperatures, here even though air is warming, it's colder air, so it's not as warm as here, so you have high pressure. So two different things: warming and rising air and low pressure, sinking and warming of the air because of compression, but high pressure because this air is still sinking and is colder. Okay, so we'll come back to that and add a few more details. So here we are showing rising air expanding and cooling, so 32 degrees centigrade, rising, cooling to 22, 12 degrees, 2 degrees, and sinking air going from 2 to 12 to 22 to 32. Not always so adiabatic, not so reversible, but this is a good way to think about rising, expanding, sinking, and cooling. So we'll add a little bit more details to that as we go along. For example, if air is forced to rise because of a mountain, it will cool and expand and cause rain on this side, and the air flows over and begins to sink and warms on the other side because the moisture has been squeezed out. So you will get heating at dry adiabatic rate and cooling at wet adiabatic rate. So we have introduced terminology here which we will expand on later on. So let me leave this podcast here since it's already long enough. But the term adiabatic is critical. It just means that the air parcel is moving so fast that it's not mixing with the surrounding environment and the air, so it can maintain its energy and heat as it goes up and down. So that's kind of a very subtle concept, but just think of it as an air parcel that's not getting mixed around and losing its energy or gaining energy. It's going along with its own energy, with its own water vapor condensing, expanding, condensing, and then sinking. It's compressing and acquiring heat because of compression. Again, relation between pressure, temperature, and density. Okay, so we'll leave it here and come back and add more details in the next podcast.